Picture this. A woman named Jeanne Calment sits in her apartment in southern France, sipping olive oil she pours over practically everything, and calmly informs a reporter that she's outlived her own attorney, an attorney who, decades earlier, had agreed to pay her a monthly sum in exchange for inheriting her apartment once she eventually passed away, banking on the fact that she was already elderly and surely wouldn't last much longer. She lived to 122. He died before she did, having paid her for years longer than either of them ever expected. This isn't some medieval legend or exaggerated internet trivia. This is a documented, verified case, and it raises a strange question buried underneath the surface of a story like this. If a death certificate can say someone died of old age, what does that actually mean biologically? Is old age itself a real cause of death, or is something else always secretly pulling the trigger behind the scenes? Let's dig into this properly because the answer turns out to be one of the more fascinating, occasionally frustrating rabbit holes in modern biology. Let's start with something that might surprise you. Despite how casually we throw around the phrase died of old age, it isn't actually recognized as a specific, standalone medical cause of death, at least not in the way a heart attack or pneumonia is. Death certificates require a defined physiological reason for death, something a coroner or physician can point to as the actual mechanism that stopped the body from functioning. Old age alone doesn't satisfy that requirement because old age itself isn't a disease or an event. It's a description of accumulated risk. Saying someone died of old age is a bit like saying a car stopped running because it was old, when in reality something specific failed, whether that's the engine, the transmission, or a dozen small parts finally giving out simultaneously after decades of wear. This distinction matters enormously once you start examining it closely because it reframes the entire question we're exploring today. Nobody technically dies purely from the passage of time. What actually happens is that aging creates a slowly worsening environment inside the body, one where organs become increasingly fragile, immune defenses weaken, tissues lose their ability to repair themselves efficiently, and the margin for error shrinks dramatically. Within that fragile environment, something eventually breaks, a blood vessel ruptures, an infection overwhelms a weakened immune system, a heart finally can't keep pace with the demands placed on it. That specific breakdown becomes the official cause of death. Old age is the backdrop, not the trigger. So why does this distinction actually matter beyond simple paperwork technicality? Because it opens up one of the most fascinating questions in modern biology and medicine. If aging itself isn't technically what kills you, but rather the vulnerabilities aging creates, then, theoretically, could you interrupt or slow that vulnerability-building process enough to prevent those underlying triggers from ever occurring in the first place? This is exactly the question driving an enormous, rapidly growing field of scientific research, and it's why serious scientists, not just fringe biohackers or wellness influencers, are increasingly treating aging itself as something that might eventually be classified as a treatable condition rather than an unavoidable inevitability. Let's dig into what's actually happening inside your body as it ages, because understanding the mechanics here makes everything that follows considerably more interesting. One of the most well-studied aging processes involves something called cellular senescence. Throughout your life, cells divide repeatedly to repair tissue, replace damaged components, and keep your body functioning. But cells can't divide indefinitely. Each time a cell divides, protective caps on the ends of your chromosomes, called telomeres, shorten slightly. Eventually, after enough divisions, these telomeres become so short that the cell can no longer safely divide without risking genetic damage, so it enters a state called senescence, essentially retiring from active duty while still technically remaining alive within your tissue. Here's the problem. Senescent cells don't just quietly sit in the background doing nothing. They actively release inflammatory signals that can damage surrounding healthy tissue, essentially becoming disruptive retirees who refuse to leave the building and instead start causing chaos in the break room. As you age, senescent cells accumulate throughout your body in increasing numbers, contributing toward chronic low-grade inflammation that researchers increasingly believe plays a significant role in nearly every major age-related disease, from cardiovascular disease toward Alzheimer's, toward various cancers. This phenomenon has become such a serious area of research focus that scientists have developed an entire category of experimental drugs called senolytics, specifically designed toward identify and eliminate these problematic senescent cells before they can cause further damage. Now, here's where things get exciting from a research perspective. In laboratory studies involving mice, researchers have successfully used senolytic treatments to clear out accumulated senescent cells, and the results have been remarkably promising. Treated mice showed improved physical function, reduced frailty, and in several studies, measurably extended lifespan compared toward untreated control groups. This doesn't mean we've cracked immortality using laboratory rodents, but it does provide compelling evidence that at least one specific mechanism driving biological aging can potentially be targeted and at least partially reversed using the right therapeutic approach. Let's shift toward another major area of aging research, since senescent cells represent only one piece of a considerably larger puzzle. Mitochondria, the tiny structures inside your cells responsible for generating energy, gradually become less efficient as you age. This decline matters enormously because virtually every process in your body depends on reliable energy production, from muscle contraction toward brain function toward basic cellular repair. As mitochondrial efficiency declines with age, cells throughout your body essentially start running on a weaker, less reliable power supply, contributing toward the general fatigue, slower healing, and reduced physical resilience commonly associated with aging. Researchers studying mitochondrial decline have identified several compounds that appear capable of at least partially restoring mitochondrial function in aging cells, and some of these compounds are already being tested in human clinical trials. This represents significant potential since improving mitochondrial efficiency could theoretically address multiple age-related problems simultaneously, rather than requiring separate treatments for each individual symptom of aging as it appears. Now let's talk about something that tends to fascinate people specifically because it sounds almost too strange to be real: certain animals that appear to have found a way around typical aging processes entirely. Remember that immortal jellyfish we've touched on before, capable of reverting back toward an earlier developmental stage instead of simply aging toward death? While that particular case remains scientifically remarkable, it's difficult to translate directly toward human application, given how dramatically different jellyfish biology is compared toward complex mammalian systems. However, other examples offer considerably more directly relevant insight. Consider naked mole rats, creatures that, despite their unfortunate appearance, have become celebrated within aging research circles. These small rodents live remarkably long lives compared toward similarly sized mammals, sometimes reaching 30 years or more, while a typical mouse rarely survives beyond 2 or 3 years. Even more strikingly, naked mole rats show minimal signs of typical age-related decline throughout most of their unusually extended lifespan. Their cancer rates remain remarkably low. Compared toward other mammals, their cellular repair mechanisms appear considerably more robust, and researchers studying their genetics have identified several unique biological adaptations that seem directly responsible for this unusual resistance toward typical aging processes. Studying naked mole rats has provided valuable insight for researchers specifically because their biology, while unusual, remains close enough toward typical mammalian systems that findings from these studies can realistically inform potential human applications. Unlike the jellyfish example, which operates according toward biological principles considerably more distant from human physiology. Several research teams are actively studying exactly which genetic and cellular mechanisms allow naked mole rats toward avoid typical aging decline, hoping toward identify pathways that might eventually translate toward human anti-aging treatment. Let's talk about something worth appreciating regarding caloric restriction, since this represents one of the most consistently reproducible findings across aging research spanning multiple decades and multiple different species. Studies conducted across yeast, worms, flies, mice, and even some primate studies have consistently shown that moderate caloric restriction, essentially eating meaningfully less than typical while still maintaining adequate nutrition, extends lifespan and improves various markers of healthy aging across virtually every species tested. This effect appears connected towards specific cellular pathways related towards. By the way, if you want to go even deeper into the secret lives of ancient humans, I just launched a full course called The Secret Lives of Ancient Humans. 10 modules, 3+ hours of content covering everything we never talk about on YouTube. What they feared, how they communicated, what hunted them, and much more. Plus an exclusive PDF guide included. Link in the description. See you inside. Stress resistance and cellular repair mechanisms, essentially suggesting that mild, sustained dietary stress somehow triggers the body toward activate more robust maintenance and repair processes, treating scarcity as a signal toward prioritize longevity over other metabolic functions. This doesn't mean starving yourself represents some magical longevity hack, since severe caloric restriction carries health risks and definitely shouldn't be attempted without proper medical guidance. But the consistency of this finding across such a diverse range of species has made it one of the most scientifically respected areas within longevity research, and it's directly inspired the development of several pharmaceutical compounds specifically designed toward mimic the beneficial cellular effects of caloric restriction without actually requiring someone toward dramatically reduce their food intake. One such compound, rapamycin, has generated enormous scientific interest specifically because it appears toward activate similar cellular pathways as caloric restriction, essentially tricking cells into believing they're operating under mild dietary stress even when normal food intake continues. Originally developed as an immunosuppressant medication for organ transplant patients, rapamycin has shown promising results in extending lifespan across multiple animal studies, and ongoing human trials are actively investigating whether these benefits translate safely toward human application as well. Now let's shift toward something worth exploring regarding genetics specifically, since certain rare human populations have provided researchers with valuable natural experiments regarding longevity and aging resistance. Researchers studying populations with unusually high concentrations of individuals living past 100 years, sometimes called longevity hotspots, have identified specific genetic variants that appear considerably more common within these populations compared toward the general population. Some of these variants appear connected toward more efficient cholesterol processing, others toward enhanced cellular repair mechanisms, and still others toward improved immune system regulation that seems to reduce chronic inflammation throughout life. Studying these naturally long-lived populations offers researchers valuable insight precisely because it demonstrates that human biology already contains examples of genetic variation capable of meaningfully extending healthy lifespan under real-world conditions, rather than purely theoretical laboratory possibility. This has inspired considerable research interest specifically focused toward understanding whether these naturally occurring protective genetic variants might eventually inform gene therapy approaches capable of providing similar protective benefits toward people who weren't fortunate enough toward inherit these particular genetic advantages naturally. Let's touch on something fascinating regarding stem cells and their potential role within future anti-aging research, since this represents another active, rapidly developing area of scientific investigation. As you age, your body's supply of active, healthy stem cells, the cells responsible for regenerating and repairing damaged tissue throughout your body, gradually declines both in total number and in overall functional effectiveness. This decline contributes significantly toward the reduced healing capacity and increased frailty commonly associated with advanced age, since your body simply has fewer reliable resources available toward repair ongoing wear and damage as effectively as it once could during youth. Researchers are actively exploring several different approaches toward addressing this specific aspect of aging, including techniques for reprogramming existing cells back toward a more youthful, flexible state, and methods for introducing fresh, healthy stem cells directly into aging tissue toward help restore more effective repair capability. Some experimental approaches have shown promising results in animal studies, including partial reversal of certain age-related tissue damage, though translating these findings safely and effectively toward human treatment remains a considerably more complex challenge still being actively worked through within ongoing research. Now here's something worth pondering that connects directly back toward our earlier discussion regarding what actually appears on a death certificate. Even if researchers eventually succeed in significantly slowing or partially reversing several of these underlying aging mechanisms, senescent cell accumulation, mitochondrial decline, stem cell depletion, chronic inflammation, this wouldn't necessarily mean death itself becomes entirely optional. It would mean the specific triggers that currently cause death, heart failure, stroke, cancer, organ failure, might occur considerably later in life, potentially allowing people to remain healthy and functional for meaningfully longer periods before eventually encountering some other specific cause of death. This distinction matters enormously for understanding what realistic longevity research actually promises versus what science fiction sometimes implies. Nobody serious within this research field is promising literal immortality. What they're actually pursuing is something researchers often call health span extension, meaning extending the number of years someone remains healthy and functional, rather than simply extending total lifespan while potentially prolonging years spent suffering from chronic illness or severe frailty. This distinction represents an important ethical and practical consideration within the field, since simply extending total years lived without corresponding improvement in quality of life during those additional years would represent a considerably less appealing outcome compared toward extending healthy, active life. This evolutionary perspective actually offers something hopeful for longevity researchers, since it suggests aging isn't some unavoidable, fundamental law of physics that absolutely must occur. Instead, it represents a byproduct of evolutionary priorities that happened toward favor reproduction and early survival over indefinite bodily maintenance. If aging emerged primarily through evolutionary priority rather than fundamental physical necessity, this theoretically means it's the kind of biological process that could, at least in principle, be modified or adjusted through sufficiently sophisticated medical intervention, rather than representing some absolute unchangeable law that no amount of scientific advancement could ever meaningfully address. Let's touch on something worth exploring regarding specific promising research directions currently generating serious scientific excitement, since this helps ground our discussion in tangible, ongoing developments rather than purely abstract theoretical possibility. Beyond senolytics and rapamycin, researchers are actively investigating partial cellular reprogramming, a technique that essentially resets certain aging markers within cells back toward a more youthful state, without completely erasing the cell's specialized identity and function. Early studies using this approach in mice have shown remarkable results, including partial reversal of age-related vision loss and improved overall tissue function, though researchers remain appropriately cautious regarding safely translating these techniques toward human application, since imprecise reprogramming carries risk of triggering uncontrolled cell growth, essentially raising legitimate concern regarding potential cancer risk if this technique isn't refined with extreme precision and safety. Another active research direction involves NAD+ precursors, compounds that support a crucial cellular process involved in energy metabolism and DNA repair that naturally declines as you age. Some early human trials investigating NAD+ supplementation have shown modest but measurably positive effects on certain markers of cellular health, though researchers generally caution against overly optimistic interpretation of these early results, since human aging research notoriously takes considerably longer toward produce definitive conclusions compared toward faster reproducing laboratory animals like mice or worms. Now let's consider something worth appreciating regarding the complexity and difficulty involved in human longevity research specifically, since this helps explain why definitive answers regarding human anti-aging treatment remain considerably further away compared toward the more dramatic headlines occasionally suggesting imminent breakthrough. Mice typically live only 2 or 3 years, meaning researchers can observe an entire lifespan's worth of aging-related data within a relatively short, manageable research timeframe. Humans, by frustrating contrast, typically live 70, 80, or more years, meaning definitively proving whether a specific anti-aging intervention actually extends healthy human lifespan requires either enormous patience, spanning multiple decades of careful observation, or reliance on shorter-term biological markers that researchers hope, but can't fully guarantee, actually correlate reliably with long-term lifespan extension. This research challenge explains why, despite exciting laboratory results in shorter-lived species, definitively proving comparable results in humans remains considerably more difficult and time-consuming, meaning legitimate scientific caution regarding premature claims of proven human life extension remains warranted, even while research continues actively progressing across multiple promising directions simultaneously. Let's touch on something worth appreciating regarding the ethical and societal dimension of this entire discussion too, since meaningfully extending human health span raises significant questions extending well beyond pure biological feasibility. If researchers eventually succeed in meaningfully extending healthy human lifespan, this would likely raise complex questions regarding resource allocation, retirement systems, population growth, and equitable access toward these potentially expensive treatments, since there's concern that early anti-aging treatment might initially remain accessible primarily toward wealthy individuals capable of affording cutting-edge, expensive medical intervention, potentially creating troubling new dimensions of healthcare inequality beyond what already exists today. These important ethical considerations don't diminish the legitimate scientific value of longevity research, but they do represent serious questions that researchers, policymakers, and society more broadly will need toward carefully consider as this research field continues advancing and potentially producing viable human applications in coming decades. Let's wrap up by returning toward our original question and considering what we've actually learned throughout this exploration. Can you really not die of old age? Technically, no, in the strict sense that old age itself isn't a specific physiological mechanism capable of directly ending life. Something specific always ultimately fails. A heart, a blood vessel, an organ system overwhelmed beyond its capacity toward continue functioning. But this technical distinction opens up something exciting rather than simply representing dry medical semantics, because it suggests aging itself functions considerably more like a modifiable risk factor than an absolute, unchangeable inevitability. The various mechanisms we've explored throughout this discussion, senescent cell accumulation, mitochondrial decline, stem cell depletion, chronic inflammation, genetic factors influencing longevity, all represent specific, identifiable biological processes that researchers are actively working toward, understand, and potentially address through increasingly sophisticated medical intervention. This doesn't mean immortality sits right around the corner, waiting to be casually unlocked within the next few years. Human biology remains complex. Human lifespans remain long compared toward typical laboratory research timelines, and definitively proving safe, effective human application for many of these promising early research directions will likely require considerably more time, patience, and careful, rigorous scientific study before reaching reliable real-world application. But the fundamental scientific perspective has shifted in recent decades, moving away from treating aging as simply an unavoidable, unchangeable fact of biological existence, and increasingly treating it instead as a complex but potentially modifiable biological process. Similar toward how medical science has already successfully identified and addressed specific mechanisms driving other conditions once considered simply inevitable aspects of human existence. Whether this research eventually produces dramatic human lifespan extension, or more modestly succeeds primarily in extending healthy years while modestly reducing prolonged periods of frailty near life's natural end. Either outcome would represent meaningful scientific progress worth taking seriously. Next time you hear someone casually mention that a relative died of old age, you'll now understand there's actually a specific, identifiable biological mechanism hiding behind that casual phrase, one that researchers worldwide are actively working toward understand more deeply and potentially, eventually, meaningfully delay. Jeanne Calment sipping her olive oil and quietly outliving the attorney who bet against her wasn't simply lucky regarding some mysterious, unexplainable resistance toward old age itself. She was navigating the exact same specific biological mechanisms we've explored throughout this discussion, mechanisms that happened for reasons researchers still don't fully understand even today toward operate somewhat more favorably within her particular biology compared toward most other people who've ever lived.